Welcome back, dear children. Today we will be continuing chapter 14, Solids and Semiconductor Materials. Lesson 2. Today's objective is semiconductor. In the previous lesson, we have discussed about the formation of energy bands. And we also distinguished between semiconductors, metals, and insulators based on energy band theory. And also we distinguish it on the basis of their conductivity. So semiconductors, conductivity is in between that of conductors and insulators. Now we are classifying semiconductor mainly to two different types. So semiconductor classified into two categories. First one is called intrinsic semiconductor. Second is extrinsic semiconductor. Now, intrinsic semiconductor. These are the semiconductors in their pure form. So, intrinsic semiconductor is semiconductor in its pure form. But the conductivity of pure semiconductors is less. We can enhance the conductivity by adding suitable impurities to it. This process is known as doping. Such doped semiconductors are called extrinsic semiconductors. So intrinsic semiconductors are semiconductors in pure form. Pure form. Extrinsic semiconductors, they are doped semiconductors. So what is doping? Conductivity of intrinsic semiconductors are small. So we can increase their conductivity by adding suitable impurities. This process is called doping. Example of semiconductor is in pure form. We can consider silicon, germanium. These are the two examples. Many examples, I am giving only two examples. So semiconductors are classified into two types. Intrinsic semiconductor, extrinsic semiconductor. Okay. Intrinsic semiconductor means semiconductors in its pure form. Extrinsic semiconductor, they are doped semiconductors. What is doping? Doping is the process of adding suitable impurities to pure semiconductor to increase the conductivity. Doped semiconductors are called extrinsic semiconductors. So what is doping? Adding suitable impurities to pure semiconductor to increase conductivity. That is known as doping. Now, before we are coming to doped semiconductor or extrinsic semiconductor, before we go to extrinsic semiconductor, we are going to discuss intrinsic semiconductor further. Now, we are going to learn about the charge carriers in an intrinsic semiconductor. Okay, charge carriers in semiconductors. Okay, so charge carriers in semiconductors. Charge carriers in semiconductors. You consider a pure semiconductor. Example, germanium or silicon. You know, number of outermost electrons for silicon and germanium is 4. Their valency is 4. So in a germanium crystal or silicon crystal, each atom make covalent bond with the neighboring 4 silicon atoms, because they have 4 electrons in the valence outermost shell. So they share 4 electrons and make a covalent bond. Okay. Now what happens is, due to temperature, you know, as temperature increases, the atoms vibrate, or we can say crystal structure vibrate. Then bond will be broken. Electrons gain, vibration of electrons increases, they gain more kinetic energy, they can become free. So bond will break. This process is called thermal agitation. So due to thermal agitation, covalent bond break. Suppose one bond is broken. When a bond is broken, you can see one electron will come out of the bond. 2 electrons are in a bond. When the bond is broken, 1 electron come out. Okay. And from the place electron come out, there will be a vacancy of an electron. This vacancy is known as hole. H-O-L-E, hole. So what is a hole? Due to thermal agitation, covalent bond break. Suppose a bond is broken, 1 electron come out, and in that place of the electron, there is a vacancy. That vacancy is known as hole. Okay, consider electron as you are sitting on a chair. When you move out of the chair becomes vacant. The same way, this vacancy of an electron is known as hole. So when a covalent bond break, 1 electron will be created, 1 hole will be created. The hole behaves exactly like a positive charge. So charge is neutralized only. Okay. Now, some other bond in the crystal may break. Then also 1 electron come out. This electron go and fill the previous hole. The new hole appears at the present site. So the hole is shifted to a new location now. So the hole can move throughout the crystal. Hole moving means positive charge is moving. This constitutes a current called hole current. Similarly, I told you when first bond broken, 1 electron is free, it can move throughout the crystal structure. So electrons moving, that constitute electronic current. So in a semiconductor, there are 2 types of currents, electron current and a hole current. Total current will be same. So sorry, sum of the 2. Total current will be sum of electron current and a hole current. So what is a hole? Hole is the vacancy of an electron. How a hole is created? Due to thermal agitation. Okay. So what are the charge carriers in a semiconductor? First one is electron. Second one is hole. What is a hole? Hole is the vacancy of an electron. Hole is the vacancy of an electron. Hole behaves like a positive charge. Exactly like a positive charge. Now, how these electron holes are generated? How they are generated? I already explained. Due to thermal agitation. Okay. So we can consider a silicon crystal. You know, valency of silicon is 4. Silicon or germanium. You can take any one of this. You know, silicon has 4 valence electrons. So this is a silicon. So this silicon forms covalent bond with the 4 neighboring silicon atoms in a crystal. Okay. This is one silicon atom. So this continues throughout the crystal structure like this. Another silicon atom. This will continue throughout the crystal structure. This will continue. Suppose one bond is broken due to thermal agitation. Suppose this bond is broken. I will write with the this bond is broken. This bond is broken. So you can see that one electron comes out And here there is a vacancy created. This vacancy is known as hole. Now, some other bond in a different location breaks. Suppose this bond is broken. So a bond in a neighboring location is breaking. Then what will happen? Suppose this is broken. So again, one electron is freed. Hole is created here. This hole moved to the previous site and combined with the hole there. So new hole appears at the present site. This so the hole is shifted to the present site now, second site now. This is the first site. This is the second site. So hole is moving. Now some other covalent bond break, electron is created. That electron will come and fill this hole. So new hole appears at the present site. In this way, hole can move through the crystal structure. Okay, hole can move through the crystal structure. This constitutes hole current. Okay. Due to thermal agitation, what will happen? Due to thermal agitation, a covalent bond break. An electron is freed. A vacancy is created at the site. Vacancy of electron is created at the site. This vacancy is known as hole. This vacancy of electron is known as hole. This electron is called hole. The hole acts like a positive charge. The hole acts like a positive charge. Now, a neighboring covalent bond break. Then what will happen? Electron and holes are generated. An electron and hole is generated. An electron and hole is generated. The electron moved to the previous hole. Electron moves to the previous hole. And a new hole appears at the present site. So in this way, hole can move through the crystal. The movement of hole constitutes hole current. And you know, first time when electron is created, that electron can move as free electrons. So electrons are also moving, right? So movement of electrons constitute electronic current. Movement of holes constitute hole current. Electronic current. And movement of holes constitute hole current. Movement of hole constitute hole current. So sum total current is sum of these two. I equals IE plus IH. So these are the current carriers in a intrinsic semiconductor, holes and electrons. And one thing you have to remember, number of electrons and number of holes are same. Because when a bond break, holes and electrons are created in pairs. So the number of electrons per unit volume, that is known as number density of electrons. Within bracket Ne, suffix E equals number of holes per unit volume. Number of electrons per unit volume is equal to number of holes per unit volume. They are equal. We can write this Ne equals NH equals Ni for a semiconductor crystal. We call it as Ni. Ni is known as intrinsic carrier concentration. Ni is called intrinsic carrier concentration. Intrinsic carrier concentration. So, what are the two types of charge carriers? Electrons and holes. How electrons and holes are created? Due to thermal agitation. Okay. Electrons and holes are generated in pairs. So number density of electron and holes is same only. Crystal structure is neutral only. These are the two type of charge carriers in an intrinsic semiconductor. So today we learned classification of semiconductors as intrinsic semiconductor and a extrinsic semiconductor. What is intrinsic semiconductor? It is semiconductor in its pure form, but its conductivity is low. So to increase the conductivity, what we have to do? We have to add suitable impurities. This process is called doping. Doped semiconductor is known as extrinsic semiconductor. And based on the dopant, extrinsic semiconductor are further classified into P-type and N-type. That we will discuss next class. And we learn type of charge carriers in a semiconductor. What are the type of charge carriers? Electrons and holes. What is a hole? Vacancy of an electron. It behaves like a positive charge. How they are created? Electrons and holes are generated due to thermal agitation. What is thermal agitation? Due to temperature, electrons vibrate or crystal structure vibrate. Then bond will be broken. When a bond is broken, one electron come out of the crystal, that bond. Then there is a vacancy of an electron is created. This is hole. Holes and electrons are generated thermally. So total current is sum of the hole current and the electronic current. And I explained already how hole is moving through the crystal structure. Okay. And one more thing I have to do, energy level diagram of intrinsic semiconductor. This already you have drawn. Conduction band and valence band, you know. So valence band. This is valence band. VB. On the top, conduction band. CB. But conduction band is empty at absolute zero. So these are the energy levels. These lines are the energy levels. Here electrons are there. You know, one level, 2 electrons. So at absolute zero, conduction band is empty. But at room temperature, above absolute zero, what will happen? Covalent bond break. Some electrons will move to the conduction band. So we can draw the valence band here. Here you can see, draw the energy levels. The lines means energy levels. Here you can see some electrons raised in the conduction band. Many levels are there. So this is conduction band, valence band. So some of the electrons left from here. So holes. Suppose one electron is here, then one electron will be here. That holes in the valence band shows that electron from there is shifted to conduction band. Okay. So children, we will stop today. Remaining next class.